Hi, we are going to need to talk about continuity of a function at a point. So we generally by now have an understanding of what it means for a function to be continuous. As you follow along the graph, you shouldn't have any breaks or jumps. But what's the formal thing? So if you consider an arbitrary function f of x, it's going to be continuous at some point c when all three conditions are met. First of all, the limit of f of x at x equals c must exist. The function must be defined at c, and the third condition is going to tie it all together is the limit and the function are going to equal each other. Please keep in mind that all three conditions must be met. At least one of them fails, the function is not going to be continuous at c. And the limit, the condition number 1, actually it should say condition 1, is going to require that the limit from the left and the limit from the right are going to equal each other, which is what this statement here says. Okay, so let's take a look. First of all, let's take a look at some graphs and understand what the problems are. So the function number 1, what is the issue here? The issue here is if you compare left and right hand limit, they are not going to equal each other. So the limit, if you consider this f of x and this point is 1, as x approaches 1 of f of x does not exist. What is the issue with the second graph? The limit here exists, as you can see, you approach the same value from left and right, but the function is not defined. So here f of 2 is undefined. Okay, and what is the issue with the third graph? This is the one that happens quite often, that the limit exists, because you can see that from both sides you're approaching the same value. The function also is defined because there is a point that matches this value of 2, but they are not going to equal each other. So here the limit as x approaches 2 of f of x does not equal f of 2. They're different values. So these are three situations that you can run into when you try to determine if a function is continuous at a point. Alright, so examples. So we're going to do it analytically now. We need to determine if this function f of x equals x squared plus x is continuous at x equals 1. So we need to check all three conditions. You probably already have a solid understanding of one-sided limits by now, so I think I'm not going to go through the details here. This function does have limit. Direct substitution will work here, so the limit as x approaches 1 of f of x, in this case, is going to simply substitute it, it's going to equal 2, right? Condition number 2, so let's number that. Condition number 2 requires us that f of 1 exists, which it does, and it is going to be direct substitution. It's also going to equal 2. We can see that the limit as x approaches 1 of f of x is going to equal f of 1. So f of x is continuous at x equals 1. Alright, but this is a pretty this is not a situation you're going to see a lot, because this is a function that you probably would know is continuous, but because it's a polynomial functions are continuous. In this case it's a quadratic function, so a lot of times you're going to see functions that are going to be piecewise functions, and then it gets a little tricky. So let's take a look at this example 2. So what do we have here? We have this piecewise function, and each function individually, this is a linear function, this is a quadratic function, each one of them is continuous everywhere, but the question is what's going to happen at 3? So what we need to do is we need to first take a look at the limit. So the limit as x approaches 3 from the left of g of x is going to be determined by this function here, and you can use direct substitution here. So 2 times 3 minus 1, that is going to be 5, right? 6 minus 1 is 5. And for the for the right hand limit, the limit as x approaches 3 from the right of g of x is going to be, so we substitute 1 here, that is also 5. So from there we can conclude that the limit as x approaches 3 of g of x is going to equal 5. So that's good, limit exists. How about the function? Well, can we substitute the value of 3 into the function? Yes, we can. We substitute into the first one because that's where equality is. So that is also 5. And since the limit and the value of the function are the same, we can conclude, let's write this first, so the limit as x approaches 3 of g of x equals g of 3. So g of x is continuous at x equals 3. Okay, let's move on. Example 3. What about this function? So we're going to have to run through the same process. So the limit, number 1, the limit as x approaches 2 from the left of h of x, again it's a piecewise function, so we're going to be determined by this here. So it's 2 plus 1, which is going to give us 3. Then the limit as x approaches 2 from the right, so approaching 2 from the right, we're going to be using this one, the second equation. So that is going to give us 0. This is probably the nicest situation because we're checking the first condition. That will allow us to conclude that the limit as x approaches 2 of h of x does not exist. What's nice about this, you don't have to go ahead and check any of the other conditions because it would not matter. Two limits are different. I mean, one-sided limits, the limit does not exist, not continuous. Okay. Example 4. So start with the limits. The limit as x approaches, so 2 from the left of f of x. So we use the first equation because that's where less is. So 2 plus 1 is 3, right? For the right-hand limit, the limit as x approaches 2 from the right is going of f of x is going to be determined by the third equation because that's where greater is. So it's going to be 5 minus 4, which is also, well, which is not also, which is 1. So the limits are different. We don't need to check anything else. It's not going to make any difference. So the limit as x approaches 2 of f of x does not exist. So not continuous. Right? But that's not always going to be the case. Most of the time, at least the limit will exist. So let's take a look at this problem. So example 5. This is a situation that we've seen before. So with equations like that, let's see if the limit here is going to exist. We actually may not have to check one-sided limits here because this function exists on both left and right of 2. The only problem is with 2. So when you try to find the limit as x approaches 2 of f of g of x, you are going to be finding the limit as x approaches 2 of x minus 2, x plus 2 divided by x minus 2. You can use dividing out. It's going to be the limit as x approaches 2 of x plus 2, and the answer is going to be 4. As you can see from the second line, we can clearly see that g of 2 is going to equal 4. We see that the limit of g of x as x approaches 2 is going to equal to g of 2 continuous. Okay. For example 6, we have a piecewise function, so we need to check this. We're going to start with one-sided limits. So the limit as x approaches -1 from the left of h of x. So we use the first equation. It's going to give us -2. Right? For the right-hand limit of h of x, plug it into the second equation, that is also -2. Therefore, the limit as x approaches -1 of h of x is going to equal -2. But here's the problem we have. You have to be very, very careful here. There's no equal -1 here. The first equation is strictly less than -1. The second equation is strictly greater than -1. You don't have equal -1. What we have here is the number 2. It's h. My apologies. H of -1 does not exist. So we have nothing to compare a limit to. It's going to be not continuous. Alright. And last thing that I want to show you here is there are very often problems when you have to determine a particular value that's going to make the function continuous. So if you ignore this last line, the function that you see above that, the function is going to be continuous everywhere except -3 because you're going to be dividing by 0. So the question is, what's going to happen? How can we define k at this point so that the function is continuous? So let's start by finding the limit. So the limit as x approaches -3 of g of x is going to be the limit as x approaches -3. We can factor we can divide out, so we're trying to find the limit as x approaches -3 of x minus 3. Direct substitution works here, you get -6. So what do we want? We want the function's value to be exactly the same. In other words, we want it to be -6. So what we want to write is we want g of -3 to equal -6 to make this function continuous. Right? And that basically means that that's going to be the value of k. Okay? So what's going to happen is if k is -6, then what's going to happen is since the limit of g of x as x approaches -3 is -6, and the value of the function is going to be defined as -6, then the function will be continuous. Any other value of k, it's not going to work. So our answer here is going to be k equals -6. Okay? And I hope this helps. See you next time.